Hello and welcome back to another video on physics. Today we're going to be taking a look at some questions of the Imat exam, which is the entrance exam to some of the Italian universities for medical purposes, things in medicine and dentistry. So the first couple of questions are about measurements in physics. So you have to know about quantities. The first one is actually saying which one is not a vector. So obviously we know that velocity is a vector, weight is a vector, charge is a vector, and the only one that is not a vector is electric field. Acceleration is also a vector. And quick reminder, vector quantities are the quantities in physics that have, basically magnitude and direction. The second one says, in the expression below, gravitational acceleration, height is h, m is mass, and blah, blah, blah. It's saying, which of the following expressions have units of power? So first of all, the first one, we have mv squared over 2 times t. Now, this looks familiar, doesn't it? Well, if it doesn't, mv squared over 2 is actually the formula of kinetic energy. Kinetic energy is 1/2 of mv squared, but you can also write that as mv squared over 2. And since this is getting multiplied by time, it's like saying this whole thing is measured in joules. We know that the unit of kinetic energy is joules. So it's like saying joules is getting divided by seconds. And we know that power has a formula of energy divided by time, which is joules per second. And eventually we can also say the actual unit of SI unit of power is just watts. So this is in fact, something that has the same unit as power. The second one is another formula of power. So this does in fact have the unit of watts or power. And the third one is just gravitational potential energy, which is just GPE divided by time. So again, it's joules divided by seconds, which is also equivalent to 1 watt. So all of them are actually expressions that have the same unit as power. So that will mean that the answer is E, 1, 2, and 3. Let's take a look at question number 3. This one says, which one is dimensionally consistent or has consistent units? If you don't know what dimensionally consistent is, which one has the consistent unit? First of all, you have to look at the left side of the equation. Energy is measured in joules, resistance in ohms, temperature change in Celsius or kelvins, acceleration is in meters per second square, and current in amperes. So you have to see whether the two things that are given, if they're getting added or subtracted or divided or multiplied, have the same unit as the left side. So all of the things. So you see over here, A, 1/2 of mv squared is a unit, we just learned about it, it's for kinetic energy. This is in joules. But F times V is another formula of power. So force times velocity. So that's measured in watts. The second one, B, this one is measured in ohms, but the other two things are measured in 1/ohms because they are saying 1/R3 or 1/R4, which is measured in ohms. So that's not consistent. So B and A is not correct so far. Temperature change, well, we know that energy is equal to mc delta T. This is the energy required to raise the temperature of a substance. If we were to rearrange for delta T by dividing both sides by mc, we would find that the change in temperature is energy divided by m times c. And so even the formula is not consistent. So of course the unit for this one is not going to be consistent, but you can also check it out. Energy is measured in joules, m is measured in kilograms, specific heat capacity is measured in joules per kilogram Celsius. So if you were to cancel these out, you would get joules square over Celsius, which is completely inconsistent with the unit of temperature change. Acceleration is in meters per second square. Let's find out the other ones. This one is 1/2 of vt squared, which is a kinematic equation, which is measured in meters per second times second square, and F over m is just newtons over kilograms, which is consistent with meters per second square, but the other unit is completely off. And so D is also wrong, which would make E the correct answer. And if you want to check it, well, we know that R, according to Ohm's law, is V over I. So I is simply V over R, which is exactly the first formula. So this is measured in amperes, and that's correct. And we also know that Q is equal to I times T. So if we were to rearrange for I by dividing both sides by T, we would find that I, which is current, is charge divided by the time, which is also consistent. Number 4, it says, which physical quantity can be measured in joules per meter? Kinetic energy is measured in joules, so that's not the correct choice. B's momentum is in kilogram meters per second. No. Power is measured in watts. No. Work is measured in the units of joules or Newton meters, so that's also a no. Force, on the other hand, well, we know that work is equal to force times displacement or distance. Work is measured in joules and force is measured in newtons times meters, which is basically the unit of distance. So if we were to rearrange this, we would find that N is equal to joules over meters. So 1 Newton is technically equal to 1 joule per meter, which would make force the correct answer. This one is rather testing your ability to understand scientific notations, such as the ones that are given here. Basically, over here, they're saying which one is what is the order of their diameter, the smallest one being the first. So, technically speaking, 0.0036 micrometers is the same as 0.0036 times 10 to the power of negative 6 meters. And this one is, well, 1650. A pico is equal to 10 to the power of negative 12. And this one, nanometers, is 1.5 times 10 to the power of negative 9. So what you have to do is you have to check to see which of these is actually equal to the smallest value. So technically speaking, 1.5 nanometers is 1.5 times 10 to the power of negative 9. If we were to kind of simplify this to one digit, we would have 1, 2, 3. And so you can kind of subtract that by, 2 more units, and you would get 1.6 times 10 to the power of, since we move the decimal places from here to here, that's 1, 2, 3. You can add to the negative 12 power there because we are moving the decimal places back and adding to the tens of the negative power. So, negative 12 plus 3 should add up to negative 11, negative 10, negative 9. So that's 1.6 nanometers, which is slightly bigger than this one. So far we established that the picometers is actually not the smallest. Let's take a look at the micrometers now. Well, that one, we have the decimal place here, and we can move this here, 1, 2, and then 3. So we can add 3 to the units of that negative 6. And so that would give us, technically speaking, 0.36 times 10 to the power of negative 9. And if we were to add this one more time, you would get 3.6 times 10 to the power of negative 10. So this one is actually the, it's not the smallest yet. Let me see if I made a mistake there. So that's negative 6. And since we're moving it to the other side, yeah, that would actually be, sorry, my bad. This would be 3.6 times 10 to the power of negative 9. So the smallest would have to be this one, 1.5 times 10 to the power of negative 9. And the second one is this one. And the third one, or the largest out of all of them, is 3.6 times 10 to the power of negative 9. So you got to be careful because here, when I move the decimal places, I forgot that if you were to move the decimal places 3 places forward, you would end up with 3.6. And since it's 3 decimal places forward, you have to subtract from the power because you're going from a smaller number and you're kind of borrowing from the negative power. So you have to add, you have to increase the negative power by the digits that you kind of borrowed from, which was 3 digits. So 10 to the power of negative 6 minus 3 would give you 10 to the power of negative 9. All right, let's move on to the kinematics questions. This one, the first one is saying, which one is not an example of simple harmonic motion? Guys, any type of simple harmonic motion is a type of motion where the kind of the oscillator or the thing that you're kind of discussing goes back to its original position, and it has a, sort of acceleration and force that is in the opposite direction. So, the motion of the moon around the earth is some sort of a harmonic motion. The ripple produced when you kind of drop a stone into a tank of water is also harmonic motion. Weight moving up and down a spring is definitely an example of a harmonic motion. We have a lot of problems involving this. Anything that is vibrating or just kind of going from one place to another in a spring, or even if it's a pendulum, it's a harmonic motion. A vibrating violin string is definitely an example of harmonic motion. This is actually an example of a stationary wave, usually for musical instruments. But the motion of a ball bouncing on the floor is not the same because, the motion of the ball eventually is going to go to a stop. Not that the other things won't come to a stop. It's just that when you're talking about the motion of a ball, the same sort of theory cannot be applied. And you don't go back to your equilibrium position per se when you're talking about a ball bouncing on the floor. So 6 is D. Now, a mass is connected to a spring and it vibrates up and down. This is a very good example for you to actually kind of understand simple harmonic motion. So imagine this is a ceiling and we've kind of attached a spring to it. And at the end of the spring, we have this mass. So what's going to happen is this mass has this equilibrium position at first where it's not moving. And at the equilibrium position, we can assume that the height is equal to 0. So it's kind of like where the GPE is equal to 0. And then, it keeps going up and down. So it's going to go up and down if you kind of push down on it and release it. So what's going to happen is at the equilibrium position, as the spring passes it barely, it's going to have its maximum speed. But when it reaches the top part, that's the maximum height. At the maximum height, it's going to have a speed of 0 because it comes to a stop and then falls down again. But at the maximum height, we have maximum gravitational potential energy, but kinetic energy is equal to 0. So where is kinetic energy equal to its maximum amount? Well, we know that kinetic energy is dependent on the square of velocity, right? So basically, at the equilibrium point where height is 0 but velocity is at its maximum amount, that's where we have the maximum kinetic energy. And as we come down again, the same situation happens because we are fully extended with the spring. You know, you can either compress or extend the spring, then the spring wants to go back again. So here we have maximum extension again, and that's where we have maximum gravitational potential energy, or in this case, because it's a spring, we have maximum elastic potential energy, but the kinetic energy would again be 0. So they're saying which one is correct. The kinetic energy of the mass is maximum halfway up. That means at the equilibrium. That is definitely correct. It's maximum in the middle. The potential energy is at maximum at the top of the mass's motion. Well, the potential energy is maximum at the top and the bottom, so that would make 2 and 3 correct, and that makes the answer A the correct choice for number 7. Let's take a look at number 8 now. It says a book of mass, blah, 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 rests on a horizontal surface. It gives us the coefficient of dynamic friction. So we know that the mass of the book is 0.4. We know the dynamic friction coefficient is 0.50. And we also know that the book is pushed with a force of 10 newtons. What is what is the question asking us, basically? They're saying, what will be the acceleration after the object starts to immediately move? Well, you have to know that F equals to m times A, and acceleration is just force divided by mass. But F is sigma F there. And sigma F means the to-go forces minus the not-to-go forces. This is something you got to keep in mind. Now, let's imagine this is the surface. We have this book here, or this object that has a mass of 0.4 kilograms. So this has a 0.4 kilograms. Keep in mind that this is going to exert the weight on the ground, and the weight of the object is mass times gravity, so it's 0.4 times 10. Keep in mind the question is saying gravity is 10, so the weight is 4 newtons. That would mean the upward force, or the normal force, Fn, is also 4 newtons. Now, the forward force, or the force that is pushing this object forwards, is actually 10 newtons, but we have to find the frictional force, Fk. We know the frictional force, Fk, is measured in mu k times the normal force. So in order to find the frictional force, you have to multiply the coefficient of friction, which is 0.50, or just 5 over 10, so Fk would be 5 over 10 multiplied by the normal force, which is 4. So that would give you 20 over 10, which is 2 newtons. So sigma F, or the resultant of forces, is 10 newtons. That's the to-go force, minus the not-to-go force, which is the frictional force, and that would give you 8 newtons. And this is equal to the mass of the object, which is 0.4, or 4 over 10 kilograms, times the acceleration. So acceleration is just going to be, if you give this a denominator of 1, multiply 10 by 8, that's 80 divided by 4. And 80 divided by 4 is equal to 20 meters per second, which would make choice, meters per second square, by the way, choice D the correct answer. Let's go ahead and take a look at number 9. Now, this is an example of, right off the bat, you know this is an example of centripetal force and centripetal acceleration question, so you have to write their formulas down. F is equal to mv square over r, and acceleration is equal to basically v square over r. Now, when it comes down to centripetal acceleration and force, technically speaking, you can actually find out about the values of these things by simply using their equations. And keep in mind that here, when we're asked to find the force and the magnitude of the resultant force, we can actually sort of use their formulas. But before we do that, keep in mind that centripetal acceleration and force are always in the same direction towards the center. So force and acceleration both point towards the circle. Doesn't matter where the car is, if it's at the left side, the right side, or the up part. But the direction of the velocity vector is going to be in a different direction, right? So velocity, for example, is going to be in the q direction. So that's the direction of the velocity right now, and that's it. So now, basically speaking, and keep in mind, the direction of motion, of course, circular, so it's going to go around the circle like that. That's this part here, the green arrow part, is the direction of motion. So first, they're saying direction of acceleration. The direction of acceleration is in the r part. So that would mean that choice 4, 5, and 2 two are wrong right off the bat. And of course, since the car is moving, it's going to have a magnitude of resultant force because it's moving, right? If it's not moving, then it won't have force, but it's moving, it has velocity, it has radius, and it has mass, so it definitely has force. That would make choice 3 the correct answer, which would mean the answer for this question is actually choice D. But if there is a need for you to solve the question, then you can actually do that as well. But if you just want to kind of answer it, you know that the answer is row 3, which is you have force and the direction is in R. But if you want to find the exact magnitude of the force is going to be the mass of the car, which is 1,000, multiplied by 30 meters per second to the power of 2, divided by the radius of the circle, which is 50. So these zeros cancel out, and 100 divided by 5 is equal to 20. And 20 multiplied by 900 is equal to 18,000 newtons, which can be written as 18 kilonewtons because each kilo stands for 1,000. So that's it. As you can see, you can also solve it and find the answer, or you can just kind of guess it because you obviously have force and force is not equal to 0. Let's take a look at number 10 now. It says a ball is projected vertically upwards and then falls back to its original position. Once projected, the ball experiences only a single force downwards due to the constant accelerational field. Gravitational field. Now they're saying these are 3 statements about the ball. Which of the statements is correct or are correct? When the ball is moving upwards, it loses kinetic energy and gains potential energy. Absolutely correct. So as the ball is going up, because the force of gravity is pushing down on it, it's going to lose the kinetic energy that it has, but it gains potential energy or gravitational potential energy because it's increasing its height. And when it reaches the maximum height that it can, and that's the actual point where it has the maximum gravitational potential energy. The magnitude of the ball's acceleration increases as it falls. That's absolutely wrong because gravity on planet Earth is a constant number and it's 9.8 meters per second square, whereas the question suggests 10 newtons per kilogram, so that doesn't change. No vertical forces act on the ball and its maximum height. That's absolutely wrong because the force of gravity is going to push it down, so that's why the ball comes back. So 3 is also correct. That would make choice, obviously that's obviously wrong, sorry. So that would make choice 1 the only correct answer for this question. So this one, 10, the answer is E1 only. Let's take a look at question 11. It says a car starts at point X. Let's imagine this is point X. It travels 3 kilometers east. So we can say that, let's say the right side is the east. So that's 3 kilometers. And then 4 kilometers south. And then 6 kilometers west. And then finally 8 kilometers north. So they're saying how far away is the car from point X where it has reached the end of its journey. So here's the deal. First of all, when we travel 4 kilometers up, that means right now here the distance to this part is also 4 kilometers. So this part is 4 kilometers. And then if we were to kind of imagine this to be, half of this line, then we can also assume the distance to the red point is also just 3 kilometers because we went 6 kilometers left. So the way we can find the distance to X is to connect the tip of this vector to the tip of this vector. And as you can see, we have a triangle. And this is a famous triangle which goes by the dimensions of 3, 4, 5. The answer is A, 5 kilometers. Let's take a look at number 12. It says an electrical train is traveling on a straight horizontal track. A constant resultant force greater than 0 acts on the train in the direction of the train's motion. So it's going to accelerate the train. What happens to the magnitude of the acceleration and the magnitude of the velocity of the train? So because you're actually, imposing force on the train, then you can assume that the acceleration of the train is going to, remain constant because the force is constant. However, the velocity is definitely going to increase, and that would make choice B the correct answer. Why is A not correct? Because acceleration is not going to increase, and velocity definitely does not remain constant. C is not correct because the force is in the same direction, so it's definitely going to, impose a constant acceleration, not decrease it. D is correct in the fact that acceleration remains constant, but velocity does not remain constant if acceleration is a certain value. Of course, if you have acceleration, then your speed or your velocity will increase. And E is definitely not correct because acceleration does not increase. Now, let's take a look at number 13. This question is actually pretty interesting as well. We have to look at it and see how we can solve it. It says a car is initially stationary. When a car is stationary, that means that the initial velocity of the car is equal to 0. When they say a car is a stationary, it's at rest, it starts from rest, or something is dropped, initial velocity is 0. Then they're saying the car accelerates for 5 seconds at an acceleration of 4 meters per second square for a time of 5 seconds. So right off the bat, I know what they want. They want you to find the maximum speed of the car. There you go. So they want to find the maximum speed of the car, or VF. And it also says that it continues its journey, keep in mind, for 20 seconds at constant speed. Okay, so the first thing you want to do is you want to use an example of a kinematic equation, because the first part of the motion is uniform accelerated motion. So you have to use the SUVAC or whatever type of thing equation your teacher thought you to solve the first part. So I'm going to use VF equals to AT plus VI. That's an example of a kinematic equation. VF is what you're looking for. AT is 4 and T, or time, is 5. And the initial velocity is 0. So final velocity of the car is 20 meters per second. That right off the bat makes choice C, D, and A incorrect. Now, we have the final maximum speed, but what about the next part? Now, keep in mind, it says constant speed for the next part of the journey. That means you no longer can use the accelerative motion equations of kinematics. You have to use the x equals to vt equation, which is for when you have constant speed, which is when the acceleration actually becomes 0. So you're looking for the maximum distance, or just the distance traveled. You know the speed is 20, and they're saying the time taken is 20 seconds. So 20 times 20 is equal to 400 meters. And that would make choice B the correct answer. Now, the reason it took a bit longer than expected is obviously I tried to explain the questions before I did them so that you get a better idea. But of course, once you learn how to do these, you can answer them in most of them in less than a minute, perhaps. But it really depends on your ability. Make sure you do a lot of practice. In the next videos, we're going to be taking a look at the other topics, but this is good enough for today. Take care and bye-bye.